Okay, so next we want to know what is the application of double integral that we have learned before this. So you can see that when we should apply the double integral in a real life problem. Okay, so firstly I want to show you again in general the double integral, where we have in general we have to integrate the function of x and y, where we have a dA here, okay, over the region R. So as we know that this one, we assume this one to be area, right? Area of what? Area of the region on the xy plane that we have, okay. And then so now I'm assuming that you know how to deal with the double integral in Cartesian and also in polar, where you have r and theta. Okay, now we want to look at two applications where you can use double integral to evaluate the area, okay, the area of region, the area of the region that we have. Okay, so that is the first application that we want to look. And after that, we want to evaluate the volume of a solid. Okay, a solid. So first I will show you about the area of the region. So how can we use the double integral to evaluate the area of region? Okay, so now when we talk about the region, so we have this one. This is the region. Okay, so let's say your region is circle. So you have a circular region. So you want to evaluate. So let's say you have a circle. So you want to evaluate the area of this region without using the formula, where the formula of the area of circle is pi r square, right? And the area of, let's say you have a triangle. So there is a specific formula that you know without using double integral. But now let's say you want to use the double integral to evaluate the area. So maybe you have your region is basically like we have done before this. We have maybe we have something like this, and then the region is bounded by the circle and the y equal to x. So then do we have a specific formula to evaluate the area of this region? So if we got if there is a specific formula, I'm sure that you have to find it. And then now we want to use the double integral to solve this. Okay, so what is the formula then? So now look at the general form of the double integral. So we know that this one is area. It is already area. If I ask you to evaluate the area, so it is the area of the region. Then how about the f here? If you want to use this formula, this double integral to evaluate the area, and what is the value of f that's supposed to be? Because this is already area. We are talking about the area. So this one supposed to be equal to 1. So meaning that to get the area of the region using double integral, we only have dA over the region R. That's it. Okay. So for any kind of region that we have, any kind, any shape of the region that we manage to get the limit and integrate, then we can easily evaluate the area of this particular region. Okay. So as we have here, from this definition 3.3, the area of the region is given by double integral. We have where the integral is only 1. Okay, now about the volume. So we can, for the second one, to get the volume of the solid. So you must have a solid, but you cannot get the solid from the R. I mean that if you have, I rewrite the general form of the double integral, this one, R. So this one is, you have to sketch the solid. So what is the solid and what is the region? So region is closed and bounded curve on 2D. That is region, closed and bounded curve on 2D. But solid, there is a word solid here, right? This is solid. It is a closed and bounded surface on 3D. Okay, so what is region? So region on 2D. So let's say you have a triangle. So you have this triangle. So it is closed, right? So this is called whatever inside it. So we call that as region. Okay, then I repeat, what is region? Region is a closed and bounded curves on 2D. Okay, but solid, for solid, it is closed and bounded surface. Surfaces should be more than one surface. Okay, or single surface. For example, sphere. So it should be sketched on 3D. So we have sphere, a complete sphere. So it is considered a closed and bounded solid. Just like a ball, you can touch it, right? So what else? Cuboid. So you have a closed and bounded cuboid or box. Okay. What else? Maybe at ellipsoid, cone. Okay, cone. Depends on what is the information that we have. If we just have this function, so we consider this one is open surface because it is open over here. So no specific. I just if we say that our surface is based on cone, so it is open surface. But if you say that it is a solid bounded by the cone and a plane z equal to, let's say, I have z equal to 1. Z equal to 1 and the cone of z equal to x squared plus y squared. So we know that the cone is closed by or bounded by the surface of z equal to 1. So this one is z equal to 1. So now we have a solid where we have a closed and bounded surface. But if you just have the cone without the cover, so it is open, just a open surface. So hopefully you understand the word solid and region. They must be closed and bounded. Okay. Okay, now back to the volume. So we can only evaluate a volume of the closed and bounded surface. But if it is open, so your volume is infinity, right? You cannot count it. It does not exist. Then you must be able to close it. So then we can evaluate the volume. Okay, so that's why if you want to evaluate the volume, then you must have a solid, because you know solid should be closed and bounded surface. Okay, so the formula using double integral, how can we use this? How can we use the double integral to evaluate the volume? Okay, so we consider this one to be the area, isn't it? Area. Okay, and this one is the value of z, because this one is actually z. So you are given z is the function of x and y. So this function f is actually the z. So what is z? Z is the height. Then I will show you my slide on at the beginning. I show you the parallelepiped. Hopefully it is here. So where is my parallelepiped? Okay. So in this case, you have the dx and the dy. Do you remember that I explained that before? So dx multiplied by dy, it is area. And then if we have, imagine you have a cuboid. So the length and the width and multiplied by the height and the width. Sorry, the length, the width and the height. So the height here considered as z. So this one considered as the height of the parallelepiped. So if we go back to the formula of volume, so you multiply the width, the the length, the width, and the height, and will give you volume. So that's why we can have volume. Okay. So now, meaning that how can we use double integral to evaluate the area? And you have to make sure the integral is always equal to 1. And how can you use the double integral to evaluate the volume? Then you must have the complete double integral. You should have the integral here. Okay, but you have to find it. So I will show you how can we find it, because normally from the last example or the calculation, so the f, they are all given, right? So for that calculation, actually we are not computing the volume, so we just calculate the double integral. Okay, but if they ask you to evaluate the volume, then they must give you the equation or the function which are related to the solid that you have to obtain. So in this case, normally the question will ask you to find out the solid first using the surface given. So to provide that solid, then you have to sketch. So to sketch, you have to use all the technique that you have learned in chapter 1 about the sketching of graph in 3D. So that's what I told you. You need the chapter 1 again in chapter 3, especially when you want to evaluate the double integral, and after this we will have a triple integral. Okay, so we look at the example here. Okay, we want to find the area of region. So area formula, the area using double integral. So your integral is always equal to 1 dA, where your region is on xy plane, because all the information provided is in terms of x and y. So but then we need to know what is the shape of the region that we have. So as you can see here, it is stated that the region bounded by the given equations and also must be on the first quadrant. So you have to bear in mind your region should be lying on the first quadrant. Okay, xy positive. Okay, and then it is the combination of the equation y equal to x and y equal to x squared. So then we should sketch. So we have a quadratic, and then because of only on the first quadrant, so we just take only this part, and then we have the y equal to x. So y equal to x, this is not part of the line, because we only interested on the first quadrant. Okay, so it looks like then you have to look at again where is the region that we need to shade. So the region bounded by the two curves, so the straight line and the quadratic. So obviously our R is inside here. Okay, so this is y and this is x. So we need to evaluate the area of this region. Okay, of course we don't have a specific formula to obtain this one directly, isn't it? Unless you have a circle or you have a square, easy for you to just directly evaluate the area of that particular region, but not for this. We have to use double integral. Okay, so you need to determine the limit of x and y. Okay, so there is a need for us to obtain the intersection point over here, because we want to know the limit of x and y. Okay, so this one is given by y equal to x, and this one given by y equal to x squared. Then how can we obtain the point of intersection? It looks like we should have to write 2 points. So we have to solve these two lines simultaneously, where we have x squared equal to x, and remember, don't easily simplify. Then you have to do like this, where you have to factorize. So you have x minus 1 equal to 0, and you will get x equal to 0 and x equal to 1. Okay, so now obviously we should get 2 because x0 and x1 will give you y equal to. Okay, so you can put the x values that we obtain here into either one of the equation because the answer will be the same. So let's say we choose the first because it is a bit simpler, right? So when x0, y equal to 0 and x equal to 1, y also equal to 1. So then we know that the intersection point is at the origin and also at 1, 1. So now we know that this one x equal to 1 and this one is supposed to be y equal to 1. Okay, so now we already have the region, so we already have the formula, and then the procedure to get that, we just compute the double integral, that the same procedure as we done before this, where you need to determine the limit. So from the limit you can determine, you need to determine the order of integration first, and from the order of integration you can determine the limit. So you want what kind of order that you want to choose here. You want to y function, you want to x constant or y constant. Okay, so for me, I will choose x constant. Okay, I don't want x to be function because here I have y equal to x squared. If I want x to be function, I have to modify this. I have to rearrange this way. Then I need to deal with the square root. Okay, so but then it is up to you. The answer will be the same. So now I choose dy dx. Okay, so x constant and y is function. So since I decided, or you decided to have dy dx, so you should provide the a line that will guide you to determine the correct limit where it is vertical. So as you can see, this line is lying between x equal to 0 and x equal to 1. How about y? It looks like we can see this one directly. So that is the lower bound of y, and that is the upper bound of y. So the lower bound of y located at, okay, so which line belongs to this point? Or I would say this point belongs to which line? This one, the quadratic, right? So y equal to x squared. Y equal to x squared. And then the upper bound, y equal to, so the red line here belongs to the straight line, y equal to x. So now we already obtained 0 to 1 and then x squared to x. So now we already have the complete double integral to evaluate the area. So y x squared to x dx, and then x minus x squared dx, and integrate. So you will get x squared over 2 minus 1 over 3 x cubed, 0 to 1, and then 1 over 2 minus 1 over 3 minus 0. So you get 1 over 6. And because this one about the area, so we do not know exactly the unit, so we just put unit square. So we know that we are computing the area of the region. So I put the unit square because it is about the area. Okay. Okay, look at the example 2. Find the area of the region bounded by or enclosed by the parabolic. You have, okay, example 2, you want to obtain the area 1 dA over the region and your region on y-axis plane. So maybe you might wonder why this time I put xy. So actually, if you don't want to put it, it doesn't matter. I just want to remind ourselves. I just want to remind myself that the sketching of the region here is on xy plane, because later in triple integral, where we shoot something more complicated problem, where actually your region can be on xz plane or zy plane, not necessarily on xy plane. So that's why I just put this one just to uh, make sure that, just to notify myself that the region that I have should be on xy plane. But if you don't want to put that, it doesn't matter, it's okay. I will not deduct any mark then, just to help us, to guide us. Okay. Okay, so your region based on the equation of y equal to x squared, and then the line we have just like this previous example, right? But now your line is shifted somewhere else, enclosed by, and then they don't mention that it should be on first quadrant. So looks like what we have then. Okay, so your again you have another quadratic. Okay, and then you have the straight line, positive slope, and now shifted at 2. So this is 2. Okay, and then because of they don't mention this, the region should be on first quadrant, so meaning that, yeah, you can just consider all. So it looks like the region that we have enclosed by the two curves, so this is your region. Okay, so now you want to, okay, let me write down. This one is y equal to x plus 2, and this one y equal to x squared. So here again, in terms of order of integration, I want x to be constant, which is y should be function, because I don't want to rearrange the x to be square root of y plus minus. So just I don't want to deal with the square. But if you want to choose that, so it's still okay. Don't worry. You still can solve that. Okay? I just want to make it easier. Okay, so now since I'm choosing the order of integration here is dy dx, x constant, so I have to provide the line which is vertical. Okay, so you can put many lines that you want to, just to make sure that they will always has the, along the region, you will always the same lower bound and the upper bound. Okay, so now when you look at that, so all the green lines should be lying between these 2 points, right? Where we need to find it. So you need to find the intersection line here. Sorry, the intersection point here. So how can you do that? So again, we have to solve these two equations simultaneously, where then you will get x squared equal to x plus 2, where you have x squared minus x minus 2 equal to 0. So hopefully we can get the answer from this way. So 1 minus 2 x, so I want to be so this one x squared, and this one minus 2, and this one minus 1 minus x. Okay, so then I can rewrite that equation, quadratic equation, to be x plus 1, x minus 2 equal to 0. Okay, so from here I can have x equal to minus 1 and 2. So now this one is minus 1 and this one 2. So in terms of the limit of x, I can directly find out that the lines here is lying between minus 1 to 2. Minus 1 to 2. How about the y? Limit of y. Okay, just look at closely the region that we have. So y, you read y from the bottom to the top, right? Bottom to the top. So then from the bottom, so that is the which is the lower bound. So that is the point, the first point that you can see. And that lines, that points, they are all belongs to the same line, which is y equal to x squared. So you have x squared here. Okay, and then when you going up and your terminal point is this one, this one, this one, this one, and this one, and this, all these points belongs to the line of y equal to x plus 2. Okay, so then we can have the limit of x minus 1 to 2, and y is x squared to x plus 2. Okay guys, if you have any question, then please let me know. Please ask me through the WhatsApp so that I know that you don't understand. Please give some response, okay, so that if you just keep quiet, so I have no idea whether you understand or not. Okay, so now we just proceed to evaluate the double integral to obtain the area of the region. So firstly, we integrate respect to y, so y, and then x squared to x plus 2 dx. And then when we replace, so we have x plus 2 minus x squared dx, minus 1 to 2. Okay, so we have a polynomial here, so should be no problem, right? We can just directly integrate x squared over 2 plus 2x minus 1 over 3x cubed, and then replace minus 1 to 2, and then we obtain that, so we substitute x equal to 2, so 4 over 2 plus 4 minus 8 over 3 subtracted by, so now we replace 1 over 2 minus 2 plus 1 over 3. Okay, so minus 1 squared, 1 over 2 minus 2 plus 1 over 3. Okay, so then we need to simplify. Okay, so when you simplify and evaluate all the terms, you can use just directly calculator, right? And you should get 9 over 2 unit square, because this is about the area. So we know that now the area of this region is 9 over 2 unit square.